Hello viewers, welcome back to my channel. Today's topic of discussion is on deadlock detection. But before you study this deadlock detection, you should be knowing one more term called as resource allocation graph. So why is it needed here in this topic? So let me first introduce RAG, resource allocation graph, and then I shall move on to the next topic in this session, that is deadlock detection. So resource allocation graph is used for deadlock modeling. Now whatever four conditions we have studied, those four conditions can be modeled using the resource allocation graph. What is resource allocation graph? It is simply what a directed graph, and that graph consists of any other normally a graph will have what two main components, the edges and the vertices. So suppose if you are having a graph, definitely what is that you are expecting in the graph? V stands here for vertex and E stands for edges. So there will be vertex, there will be an edge, vertices and edges. Now this vertices, one vertex will be of the type process, okay, process is a vertex, and the other vertex will be a resource. So the resource will be a second type of vertex. Two types of vertex exist in this RAG. One is the process and another is the resource. So for process, normally you have to use it with a circle notation. This is what I had shown you in the previous session also. Process P1 can be indicated like this, whereas for the resource in the graph, you are going to use a square. Then what about edges? Edges can be of two types. One can be the assign edge and another can be of what? Request edge. Now even these edges you have come across in the previous session, but now let me tell you what is the type of notation in detail. Assign edge is what? Suppose if this is the process P, for that if whatever resource has to get assigned, the edge will be having a arrow direction in this manner. So it indicates what? The resource R is assigned to process P. Resource R1 is assigned to process P1. Like this you can say. Request edge is if the process is making a request for a resource, then the edge should have a direction, arrow direction pointing towards the resource. So in this example, in this diagram, you can see that process P1 is requesting for the resource R2. So this way you have to make use of this notations only in the RAG, resource allocation graph. And even this resource, whatever I have written here as vertex, it can be of two types. One can be the single instance and another can be the multiple instance. What do you mean by single instance and multiple instance? In the system, if you have, okay, only one copy of the resource existing, then it is single instance. If you have multiple copies of the resource, then we say it is a multiple instance. Suppose if there is just one printer in the system, then we say only one single instance of that resource exists. If you have more than four printers in the system, then you have to say four instances of the printer exist in the system. For that also in the graph, you have to make use of this notation. Normally single instance, suppose if the resource is R1, you can put one dot here. It indicates what? One instance of the resource R1 exists in the system. For multiple instances, whether it is 2 or 3, you have to indicate like this, 3 dots. So we can say here 3 instances of the resource R2 exist. If at all you have 4 instances, put one more dot here. So 4 instances of the resource R2 exist. So this way you have to make use of the notations in the resource allocation graph, which you will be learning in my future session. Presently what I have to tell you is, actually the topic is deadlock detection, but before you learn deadlock detection, you should be familiar with resource allocation graph. It is a directed graph which shows the status in the system. Status is what? The processes and the resources. How many resources are assigned to which process, and which are the different processes that are waiting for other resources in the system. So this way that particular complete status you will be able to get from the resource allocation graph, and the resource allocation graph makes use of these many notations. Okay, hope this part of the session is clear to you all. Now I shall move on to the deadlock detection. So we'll check here whether by just observing this resource allocation graph whether there is a deadlock. If a RAG, that is if a resource allocation graph contains a cycle, then there is a deadlock. So you can see there is a cycle formed here. Okay, but now you have to remember one more important point. An RAG may have cycle or may not have a cycle. Okay. If it is a single instance, okay, or is it a multiple instance? That means whether this RAG is representing resources with just a single instance, or is it representing the resources with multiple instances. Suppose if it is a single instance, okay, if it is a single instance, then definitely deadlock will occur. Deadlock is sure, or deadlock will occur. Suppose if a graph is having multiple instances, still there is a cycle, we cannot give the guarantee that deadlock may happen. So we can say may or may not happen, may or may not happen. Where in which case, if RAG contains cycle, but cycle is having what? The multiple instances of the resources, then there is a possibility of deadlock, or deadlock may not happen. Whereas if the cycle is, if the RAG is having resources representing single instances, then deadlock will occur. So there is a guarantee, we can say yes, deadlock will occur. And this is one important observation for RAG. Apart from that, okay, apart from that, here if at all you have to talk on the deadlock whether occurring or not occurring, better to convert this RAG into wait for graph. Now what is wait for graph? Wait for graph will have only the processes shown in the graph. So we are not showing the different resources in the system, but only the processes. So how to convert this wait for this RAG into wait for graph? So let me just write that part also. I'll erase this. Wait for graph will have only what? So this is the first diagram. I can say it is resource allocation graph. The same resource allocation graph I am converting into wait for graph, and the wait for graph will have only the processes. We can easily say by observing the wait for graph whether a deadlock will occur or not. How? But just see here, because we are interested in showing the cycle, but from wait for graph we can say, here we are not at all able to say confidently whether deadlock will occur or not. But the same graph, when we try to convert it into wait for graph, and there in the wait for graph if you see a cycle, then you can definitely say that yes, there is a deadlock occurring in the system. So this wait for graph will have only the processes. So let me just write down first the processes as it is, then I will show the dependency here, which process is. So I am just copying down P1, P2, P3, here is P4 and here is P5. So P4 I will write here and P5 I will write here. First I have written only the processes. Now let me see here whether P1 is waiting for any process. P1 is requesting for R2. R2 is assigned to P2. That means P1 is waiting for P2. So I can show like this. Yes, P1 is waiting for P2. What about P2? Is P2 waiting for P3 or any other process, P4 or P5? P2 is requesting for R4. R4 is what? Assigned to P3. So P2 is what? P2 is waiting for P3 to complete its job. What about P3? P3 is requesting for R5. R5 is assigned to P4. So P3 is waiting for P4 to complete its job. So P3 is what? Waiting for P4. Fine. Then what about P4? P4 is requesting for which resource? R1. R1 is assigned to P1. So P4 is waiting for P1. Then what about this part of this RAG? Here you can see P2. P2 is requesting for R3, whereas R3 is assigned to P5. So P2 is requesting for R3. R3 is assigned to P5. So P2 is waiting for P5. Now if from this graph I have converted to wait for graph. In the wait for graph, check if there is a cycle. Yes, there is a cycle formed here. Look here. Then definitely we can say yes, there is a deadlock occurring in the system. So this is why just by observing RAG, we cannot give the guarantee that deadlock may or whether deadlock will occur or not, but by observing the wait for graph, and in that wait for graph if you see a cycle formed, then you can say confidently yes, there is a deadlock occurring in the system. So this is all about the deadlock modeling and how to detect deadlock using the RAG. As long as there is one single resource in the RAG, there is no problem. By observation also you can carry out. But if there are multiple instances of the resources, then you have to put that in a tabular form and then try to identify or try to detect whether a deadlock will occur or not. In this example, there is a single instance. See, if I am writing R4, it is as good as what? 1 dot and R4. If I am writing R3, it is 1 dot and R3. So there is one single instance of the resource. As long as you have single instance of the resource in a graph, you can easily carry out by just observing the graph only. But it is difficult when you have multiple instances of the graph. That's the reason you can see here, if you have multiple instances, may or may not happen. So we have to check here whether deadlock will occur or not. So that will be the topics in my future sessions. Hope you find this session useful. If you find it useful, please like, share and subscribe to my channel. Thank you. Bye bye. Take care.